Hello everyone, welcome to IIT and Gate classes. Today we're going to have a demonstration on machine design. Before starting the machine design demo, I'd like to tell you that machine design is an application subject. So this is application of strength of materials. So this subject could be proper understood only if our concepts of strength of materials are good. Right? So definitely strength of materials will be taught first, the core concepts will be made clear, then we will start the subject of machine design. Let me introduce myself. I am Anubhav Parasar. I'm a BTech from NIT Jalandhar and I have cleared UPSC two times with All India Rank 2 and All India Rank 36 with mechanical engineering. So let us first discuss the syllabus of machine design. Right? Before starting any preparation, the first thing that we should understand is what is the syllabus. Right? So as I have already said, this is the application of strength of materials. Right? So whatever we are going to, there will be a little bit of overlap with strength of materials. Right? So most of the concepts, the core concepts, you will learn it in strength of materials, and then the application part will be studied here. Now, it is not very good to call this subject machine design. The syllabus that has been provided by GATE by the IITs is not exactly for machine design. Instead, it should have been called design of machine elements. That would have been much more appropriate ti- uh, title for this subject. Right? Why so? Because we are not going to design any machine here. It is only some of the machine elements that we are going to design here. Now, what is the syllabus? So we have design for we have design for static and dynamic loading, right? We have failure theories. Again, failure theories is something which will be covered in strength of materials and it will be overlapping. Some concepts will be covered in strength of materials, the core concepts, and the application part we will see it in strength machine design. Fatigue strength and the SN diagram, right? So this can be clubbed in dynamic loading. Design of machine elements such as bolted, riveted, welded joints, right? So we'll see how to design a bolted joint, riveted joint, welded joint, right? Then shafts, gears, rolling and sliding contact bearing. Rolling contact bearing means the ball bearings, roller bearings. Sliding contact bearing means the hydrodynamic bearings, or we can say like journal bearing, right? Then brakes, clutches, and springs. So you see, the syllabus for machine design is very, very small. And it is quite easy. If you have good grasp over strength of materials, the machine design topic can be completed in a very, very short period of time. And you can score all the marks that has for the questions that has been asked. So how much marks can you expect from the subject? So definitely it varies, right? Sometimes if questions from strength of materials have been increased, right? So machine questions from machine design will have little bit less weightage. And sometimes if questions from strength of materials is less, then you might get more number of questions from machine design. So on an average, if you take the average, you can get 5 marks out of 100. So definitely, as I'm saying, this is average. This is nothing else but average, right? 5 out of 100. Sometimes it has been seen that 3, 4 marks have been asked. Sometimes it goes up to 7, 8 marks also. So on an average, you can expect 5 marks out of 100, and that too very, very, very easily. What about books? Do you need to follow any reference books? I won't suggest you uh, give time to reference book for this subject. Yes, you can purchase reference books for strength of materials, for thermodynamics, and all other subjects. But I will say the class notes will be good enough for you to get the all the marks, right, in this subject, right? So exclusively we'll teach that because you don't have much of theory here, right? Mostly it is application numericals, right? And I won't suggest any book here, but even though if you want any, I'll suggest Design of Missing Elements by Bhandari. Right, that is a good book. If you want to purchase, you can actually purchase that book. Okay. So, which topic are we going to cover today? We are going to take up design for dynamic loading and a subtopic that is stress concentration. This is what we are going to learn today, and it is very interesting topic. And I hope that you will enjoy today's demo class and take home few good learning, few good concepts. So let us start. Now, design for a missing component has to be separately done for static and fluctuating load. Any missing component, you will have to separately design for static load and for fluctuating load. What is fluctuating load? Fluctuating load is nothing else but a dynamic load. This is what the topic we are going to study. I'll explain it to you slowly, right? And what is static load? Static load is a load which does not change with time. Static load is a load which does not change with time. It does not change with time, right? Static load is a load which does not change with time. Now, if a component has to be designed for static load, there are two criteria. There are two criteria on the basis of which a component is designed for static load. Basically, this is almost covered in strength of materials, right? Whatever you study in strength of materials is basically designing against static load, you can say, right? Now, what are the two criteria? Can anybody tell me what are the two different criteria which is used to design against static load? They are strength criteria, strength criteria, strength criteria, and deformation criteria. Deformation criteria. So what is the strength criteria and deformation criteria? I'll explain this concepts will be much in it will be covered in much detail when you take strength of material classes. But yes, I will try to explain it to you in a very simple term, right? So that you can have a proper understanding of how designing is being done. So let me consider a small machine element, right? And let me say you can say this is a bar, right? Rectangular bar. Its cross section can be circular, its cross section can be square, whatever it might be, right? Now let me say uh, I'm applying a force P on this bar. I'm applying a force P on this bar from both the ends. I'm applying a force P on this bar from both the ends. Okay. So if we consider any cross section, of this bar, right? Let me consider a cross section, and if you see the stress, amount of stress in this cross section, if you want to find out what is the stress, so what will be the stress? The stress can be given by sigma, and this stress is almost constant throughout the cross section. So the stress will be given by the amount of load you are applying divided by the cross-sectional area, right? So this equation, we learn it in strength of materials, right? The amount of stress will be equal to force divided by cross-sectional area, right? And this stress, for to avoid any failure, the stress should be less than the permissible stress of the material. What is the permissible stress of the material? Now, this is the material property. How much, what is the maximum amount of stress the material? It might be steel, it might be, say, cast iron, it might be aluminium, it might be copper, whatever it might be, whatever the material is made up of. Every material will have a maximum amount of stress that it can withstand, right? So, the stress induced, right, that is force divided by area, should always be less than the permissible stress of the material. So if you know what is the value of P, is how much load you are applying, and if you know the sigma permissible, this is generally known for all different materials, you can always calculate what is the cross-sectional area A. Means how much cross-section will be safe for this rectangular bar to not fail. So this is basically strength criteria, right? This is basically strength criteria. Now, what is deformation criteria? Similarly, we have deformation criteria. So let me take the same bar, right? Let me say take the same bar, and let me say two forces P and P are being applied. The same amount of force, let me say P and P are being applied on this bar. Same amount of force P and P are applied on this bar. P. Now, because of this application of this force, definitely there will be some amount of deformation in the bar, right? So, what do I mean by deformation? Definitely, as you can see, this is a tensile force, right? The length of the bar will increase. The length of the bar will increase. Let me say the length increases by delta L. Length increases by delta L. The original length is L, and because of the force P, the length of the bar increases by delta L. Now, what is delta L? What is delta L? Now, delta L again, those I'm not getting into those concepts because it will be taught in strength of materials, right? So, delta L can be given by PL divided by AE, where P is the applied force, L is the length of the bar, original length, A is the cross-sectional area, and E is Young's modulus of elasticity. That is again a property of the material. That is again a property of the material. Okay, so again, this delta L should be, this is the deformation produced in the bar, this delta L should be less than delta L permissible. Delta L permissible. So what is this delta L permissible? See, uh, whenever we are building a machine, there will be many components like this, right? Many components, and all the components have relative motions, right? Now, because and all the components will be subjected to some amount of load, right? All the components will be subjected to some amount of load. Because of the load, these components will deform, right? Some will have elongation, some will have contraction, some will have bending, all different types of deformations will be there. And because of these deformations, there is a very good possibility that it goes and interferes in the motion of some other component. As you can see, there is a change in length. If the change in length is beyond a particular limit, it is very possible that this bar can go and come in the path of some other motion. So what will happen because of this? The machine will get jammed. The machine will get jammed. So all the deformations have particular limit. That is nothing else but delta L permissible. So what is the maximum permissible deformation possible? So the deformation produced should always be less than delta L permissible. Now, if you know what is the delta L permissible, definitely the designer will know what is the maximum deformation possible. We know what is the load being acting on the element. We know what is the length, what is the cross-sectional area. Sorry, not the cross-sectional area. Young's modulus of elasticity of the material. And from here, again, we can calculate what is the cross-sectional area. So we will compare both the cross-sectional areas obtained from strength criteria and deformation criteria, and whichever is safe, whichever is larger, right, we'll consider that cross-sectional area for designing. Okay? So basically, this is nothing else but design for static load, right? This is basically what is known as design for static load. Now, the same element, if it is subjected to fluctuating load or dynamic load, the same element, if it is subjected to fluctuating load or dynamic load. Dynamic load is a load which changes with time. The stress changes with time. We're going to see an example, right? We're going to see an example. So if dynamic load is acting on the component, the engineers, the scientists, the designers were very much confused because the materials were failing at a very small amount of stress. So the materials were feeling much below than sigma permissible. Materials were feeling, the components were feeling at a stress very less than sigma permissible. So they were not being able to understand. They were thinking, we have designed it, we have considered strength criteria, we have considered deformation criteria, and everything is fine, everything is good. But whenever the under static load, it's working completely fine, it is fulfilling its life. But whenever it is subjected to fluctuating load, it fails. The failure is very unpredictable. At a very low amount of stress, the materials are getting failed. So they started to research on it, and they found out the reason why these materials, the components, fails much below the permissible stress is the presence of stress concentration. Yes, that is this topic all about. We're going to see what is stress concentration in our coming slides, right? And how this stress concentration results in failure. That is also something we'll see. But before that, let us try to understand what exactly is dynamic loading. Right? Let us try to understand what exactly is dynamic loading. In the picture, you can see a shaft. Can you see a shaft? This is nothing else but a shaft. And you can see a rotor. This is a rotor which is mounted on the shaft. This is a rotor. Now let me say the shaft is supported by two bearings at both the ends. There is a bearing at this end and there is a bearing at this end, right? And the shaft will have its weight on of its own, right? It will have some amount of weight which will be acting in the downward direction, right? Now, because of the weight, you will be able to understand that the shaft will bend, right? The shaft will bend. So if you see, view, have a look at the shaft will bend because of the load, and it will look something like this, right? So what is the kind of stress that will be in the point A? I'm considering this as point A. So what is the kind of stress in point A? Now again, here application of strength of material comes, right? So this bending, this is nothing else but bending, and we studied in bending of beams. There the concepts will be much more clear. But you can imagine, right? What kind of stress will be there at point A? The point A will be under compression. Point A will be under compression. And what kind of stress will be at point B? Point B will be under tension. Point B will be under tension, right? Now, as the shaft is rotating, what will happen after 180 degree of rotation? Let me say the shaft rotates by how much? 180 degree. Let me say the shaft rotates by 180 degree. So what is going to happen after 180 degree? What is going to happen after 180 degree of rotation? Can you tell me? What is going to happen after 180 degree of rotation? Yes, the point B will come to the top and the point A will come to the bottom. Point B will come to the top and point B will come to the bottom. Now point B is under compression and point A is under tension. Point A is under tension. So the stresses have interchanged. The stresses have interchanged. What will happen after 180 degree of more rotation? After 180 degree of more rotation, again point A will come to the top and point B will come to the bottom. So the point A will have compression, point B will have tension. So the rotor will keep on rotating. So you can imagine if you take it one point, let me say point A. So what is the kind of stress that is acting on point A? Stress is constantly changing from tension to compression, then again to tension, then again compression, then again tension, compression, tension, compression, tension, compression, tension, compression, tension. You can see the load, you can see the load is changing with time. So I hope that you are able to understand what is dynamic loading, right? Dynamic loading is the loading when load, or you can say the stress on a component changes with time, right? So it can change in magnitude, it can change in direction, right? Whatever it is, slowly we will understand. So this is nothing else but dynamic loading. And because of dynamic loading, the materials were failing at a much less stress than that of the permissible stress. Now, scientists did some research and they found out that the reason behind his failures were nothing else but stress concentration. So, what is the stress concentration? Let us try to understand the definition of stress concentration first. So, stress concentration is defined as highly, highly localized stress. Stress concentration is defined as highly localized stress due to irregularities present in the component, and abrupt changes in cross section. Abrupt changes in cross section. Let us try to understand what does it mean, right? So let us take a component. Let us take a component. Okay. Mhm. Let us take this component. Okay. And let me say this component has a small hole. Its middle point. Small hole. So because of the small hole, you can understand that there will be abrupt change in cross section somewhere here, right? There is a change in cross section. There is change in cross section here. Because of the presence of the hole, sorry, because of the presence of the hole, there is change in cross section, right? Now let me say the stress on that hole is sigma. So what is the stress acting on the hole? The stress acting on the hole is nothing else but sigma. The stress acting not on the hole, otherwise at any other cross section, what is the stress? And you can see the stress I have marked is uniform, right? Right. This can be found out using the nominal equation for strength of materials. How to find out this sigma? Sigma is nothing else but force divided by area. But if you see near the hole, the stresses will be much higher. But if you see near the hole, the stresses will be much higher. And as you go away from the hole, the stresses becomes equal to the nominal stress. As you go away from the hole, the stresses become equal to nominal stress. So you can see here, so this is nothing else but maximum stress. So this is what I say highly localized stress. This is what I call highly localized stress due to presence of irregularity. And what kind of irregularity that is present here is abrupt change in cross section. Because of the hole, the cross section has changed, isn't it? Because of the hole, it might be drilled. A hole is drilled, right? The cross section has changed, and because of the change in cross section, the value of sigma max, right? The value of sigma max is greater than the nominal stress, right? It can be much greater than the nominal stress sigma naught. right? We say this is sigma naught. This is the case. This is the case. So this is known as stress concentration. Now, what are the main reason for stress concentration? One of the reason you have already seen, that is abrupt changes in cross-section area. Cross-section. Abrupt change in cross-section. What are the other reasons of stress concentration? Variation of properties. Properties of material. Definitely all the material will not have complete uniform properties. There will be some amount of variation, and because of this variation, right, there is possibilities of stress concentration. Load application. Now, whenever you are applying a load, the load can be point load or it can be distributed load. So if it is a point load, the point at which the load is being applied, the stresses will be much greater, right, than that given by the equation of strength of materials. So because of load application, right, then because of presence of impurities, we all know there will be some amount of impurities in the components. So because of the presence of the impurities, there will be stress concentration, right? And we have machining stresses. All the components, they will be machined, right? So whenever we are doing machining, whatever machining it might be grinding, it might be turning, it might be facing, it might be any operation on lathe or any drilling, milling, whatever it might be, right? So there is possibility of stresses. So because of the stresses, there is high chances that we have stress concentration. And this stress concentration is why the materials fail. Slowly we'll keep on relating each and everything and we'll understand, right? Now the two major, if you want to measure stress concentration, you will have to quantify it, right? It's not enough to just say theoretically presence of highly localized stress, right? You have to quantify it. You have to give a number to it, right? So that is why quantity, which is known as stress concentration factor, has been defined. A quantity known as stress concentration factor has been defined. So what is the stress concentration factor? Kt. Now Kt can be given by Kt is equal to Kt is equal to is equal to highest value of actual stress near discontinuity highest value of actual stress near discontinuity divided by nominal stress obtained by strength of material equation. The highest value is the highest value of actual stress near the discontinuity. That is, we can say this is nothing else but sigma max, right? Divided by nominal stress obtained by some equation, that is sigma naught. Sigma naught. What is the value of sigma naught? Sigma naught can be simply given by force divided by area. Right? Sigma naught is the nominal stress, which we generally obtain by equation of Strom, right? And highest value of sigma max is the maximum value of stress near discontinuity. Similarly, you can also give it for shear stress. We can say tau max is maximum stress near the discontinuity divided by tau naught, which can be calculated using the equations of strength of materials. Okay, but how to obtain the sigma max, value of sigma max? So we have quantified, we have given, so we can compare now stress concentration. Stress concentration is more or less. You can compare it using the value of Kt. If the Kt is more, we can say more stress concentration. If Kt is small, we can say less stress concentration. Now, but for that, you have to find out the actual value of sigma max or tau max, right? Now, nominal stress, sigma naught, tau naught can be easily found out using equations of strength of materials. But how to find out sigma max or tau max? For that, we have done a lot of, not me, scientists, researchers, right, have done lot of experiments, and they have formed different graphs, right, and they have quantified the value of Kt there. They have quantified the value of Kt there, right? So using those graphs, right, which are available in your design data book, we can actually find out the value of K, right? So now the graphs will not be available for each and everything, because it is not possible to quantify stress concentration for machining scratches, right? Impurities, it's not possible. But mainly the graphs are for uh, abrupt changes in cross section. So if the cross section changes by this amount, and right, then what will be the value of stress concentration factor? It can be easily found out by graph, but it is not required for gate purpose, because till now never have get asked questions with respect to graph. But there's something good if we know. Now, what is the effect of stress concentration on ductile and brittle materials? Again, proper definition of ductile and brittle materials will be studied in strength of materials, right? But I'm giving you an idea so that you can have a little bit of understanding. What are ductile materials? Ductile materials are those materials which, on application of force, have considerable amount of elongation, which on application of force have considerable amount of elongation, right? For example, steel, copper, right, plastic. If you apply force, what will happen? There's considerable amount of deformation, to be precise, right? Lots and lots of deformation. But what are brittle materials? Brittle materials are those materials which does not have much deformation, right? Deformations are very less. Deformations are almost nil, very less. For example, glass, stone, brick, concrete. So you cannot have deformation, right? Can you deform glass by applying force? No. You cannot bend, you cannot elongate. Those are brittle materials. It will break off, right? What are ductile materials? For example, let me say I'm giving you a layman example. Plastic. We can apply force and you can definitely, not all plastic though, right, but you can apply force and you can deform the plastic, right? Similarly with steel, right, copper, aluminum, we can all deform all these things, right? So those are known as ductile materials. Now, on the static load, the ductile materials on the static load, the ductile materials are not affected, right, are not affected by stress concentration. Not affected. Why not? Because of their capability of plastic deformation, right? The ductile materials have the capability of plastic deformation, and because of this plastic deformation, what happens is that the discontinuities, the stress concentration, it gets dispersed, it gets distributed. There might be some stress concentration, but as we are applying force, if the material deforms, what will happen to the stress concentration, right? It will get dispersed, right? It will move to different, it will get broken, and it will move to different areas, right? And the stress concentration goes away, right? And that is why it is not much effect. We don't have much problem. That is why we are not designing uh, for static load. We have never considered stress concentration, right? Static load, we study it in strength of materials, but for designing, we've already seen it in our first slide. While designing for static load, right, we have not considered stress concentration. But under fluctuating load, or you can say Dynamic load, the endurance limit of ductile material. Endurance limit is the quantity we use for is the maximum stress amplitude, right? We use for fluctuating load. We'll see this, right? So this is again a property of the material, endurance limit. We'll see in our future slides, right? So endurance limit of ductile materials are highly reduced, highly reduced, highly reduced. Yes, that is why we have to study and stress concentration for fluctuating. And what about for brittle materials? Now, stress concentration is harmful for brittle materials for both static and dynamic load because of incapability, like it's or inability to plus to deform plastically. Inability to deform plastic, right? So brittle materials does not have the capability to deform, so the stress concentration cannot get dispersed. So that is why on the both static and dynamic loading, uh, we have to use stress concentration. So why we have not used stress concentration in static loading? Because generally for machine elements, we the mechanical engineers don't use much of brittle materials. Most of the time what we use is ductile materials. We don't use brittle materials, right? So that is why we have not considered stress consideration for static loading. But for again, even for fluctuating loading uh, or dynamic loading, the components that we manufacture or design will be always for with ductile materials, right? Brittle materials are generally used by civil engineers like concrete, like and um, to manufacture the bridges, roads, whatever, right? Those are brittle materials, and they consider um, it differently. Their designing parameters or their designs are different than that of us. Okay, now let us try to understand what are the different types of dynamic stress. This is something important. Let us try to understand what are the different types of dynamic stress. So the dynamic stress can be classified into three parts, right? Alternating or fluctuating stress, right? The first one is alternating or fluctuating stress. So what is this alternating or fluctuating stress? Alternating or fluctuating stress. Let us try to understand what is alternating or fluctuating stress. So I'm considering two axes. I'm considering two axes, right? Sorry. Hmm. So the first axis is the time axis, and this x-axis is the time axis, and y-axis is the stress axis, right? So if I consider a fluctuating stress, the fluctuating stress varies something like this. Fluctuating stress varies something like this. Okay, fluctuating stress. Okay, so I'm sorry. Yes. So fluctuating stress is something like this. Stress which varies something like this. So it will be varying this way. Again, I'm sorry. Hmm. Yes. So fluctuating stress is something which varies like this with time. Okay. So we have the minimum stress, maximum stress. As you can see, this is nothing else but the maximum stress, right? And you can see this is nothing else but the minimum stress. Right? And if you take the average, this will be the average stress, or you call it mean stress. Call it mean stress. Right? So the mean stress, minimum stress, and maximum stress. So maximum stress is represented by sigma max. Minimum stress is represented by sigma mean, right? So this is the value of minimum stress, and average stress is represented by sigma m. Right? Average stress is represented by sigma m. So you can see the value magnitude of stress is going above the mean stress to a maximum value. Then it is again coming to mean stress. Then again it is going below, right, to the minimum value. Again it is going to the maximum value. Again it is going to the minimum value. So if you take an average, you will get the mean stress. So this kind of variation, if the stress is varying this way with time, then we call it alternating or fluctuating stress. We call it alternating or fluctuating stress. Okay. Now, there is one more term that is known as the stress amplitude. What is the stress amplitude? Stress amplitude is the maximum stress above the mean stress. We represent it by sigma A. So what is the sigma A? Basically, sigma A is nothing else but the stress amplitude. Stress stress amplitude. Okay. I hope you're able to understand how the fluctuating or alternating stress varies. Okay, if you have the rest of the examples, you'll understand it much better, right? You'll have a much better clarity. So let us take now what is repeated stress. Let us see what is repeated stress. So if you take the example of repeated stress, I'll again consider two axes. We have the time axis. The x-axis is nothing else but the time axis. Y-axis is nothing else but the y-axis is nothing else but the stress axis. Now, the stress, repeated stress, varies something like this. This is how the repeated stress varies, right? I hope you're able to understand the difference, right? What is the difference between the repeated stress and alternating stress? If you take the mean value, the mean will come somewhere here. If you take the mean value, the mean will come somewhere here. Mean stress. And if you take the maximum value, this is nothing else but the maximum stress. Sorry. And you'll have the minimum stress. We can see the minimum stress, the value of minimum stress is equal to 0. The minimum stress is nothing else but it is equal to 0. So this is repeated stress. When a minimum stress is 0, so we call it repeated stress. We call it repeated stress. And again, this is maximum stress is nothing else but sigma max. We represent it by sigma max. Minimum stress we represent it by sigma mean, right? And mean stress, we represent it by sigma m. And again, we'll have the stress amplitude. Okay, stress amplitude, that is sigma a. That is nothing else but stress. That is nothing else but the stress amplitude. So this is nothing else but repeated stress, right? So this fluctuating, repeat and reverse, when you practice the numericals, right, it becomes very clear, right? We have lots and lots of numericals, right? And there are a few formulas. We will see those formulas. Before that, going there to the formulas, let us first try to complete this. Let us see what is reverse stress now. What is reverse stress? Again, we will take two axes. We have the time axis and we have the stress axis. So this is nothing else. X-axis is the time axis. Y-axis is nothing else but the stress axis. And reverse stress is something like this. Yes, I hope you're able to understand the difference between the three. You're able to understand the difference between the three. I hope that, right? So if you consider the mean stress here, mean stress is coinciding with a time axis. That is, mean stress is nothing else but 0. Mean stress is 0. This is maximum stress. This is minimum stress. The minimum stress. So here I can say for completely reverse stress, I can say sigma max, right? If I say sigma max, maximum stress is equal to minus of minimum stress, right? And if you consider the stress amplitude, right, sigma a, that is the stress amplitude, is nothing else but max, right? Stress amplitude is nothing else but equal to sigma max, right? So this three types of stress, there could be three types of dynamic stresses, and all these three stresses needs to be remembered, right? You have to practice it, and we should understand. So in question, if it is said reverse stress or repeated stress, alternating stress, things should be clear, right? What exactly, which kind of stress we are exactly talking about, right? And why it should be clear? Because designing for reverse stress is done differently, and designing for alternating fluctuating stress and repeated stress is done differently. That we will learn it in subsequent classes. Now there are a few terms that needs to be calculated. And let us see those terms. What are those terms? First is the stress amplitude, sigma A. So what is the magnitude of sigma A? Let us go back to our previous diagram and see the sigma A. So can I say sigma A is nothing else but the maximum value minus minimum value. So this will be the maximum value minus minimum value, right? This is the maximum value minus minimum value divided by maximum value minus minimum value divided by 2. So stress amplitude is nothing else but sigma max minus sigma mean divided by. Similarly, we'll have mean stress. You have to calculate mean stress. How to calculate the mean? So the formula for mean is same everywhere. If you want to calculate the mean, it is nothing else but maximum value plus minimum value divided by 2. How to calculate the mean stress? Uh, mean is nothing else but average, right? So it's a sigma max plus sigma mean minimum, sigma minimum divided by 2. Right? So these two formulas are very, very important, right? And it will be required. You will be required to recall these formulas very much, right? And the last term is the R ratio or stress ratio. R ratio or stress ratio. Stress ratio. So this can be given by the value of the minimum stress divided by value of the maximum stress. It's not just the magnitude, you'll have to do it with sign, right? With sign convention. With sign, right? So let us try to apply these formulas, right? And this are frequently used in this subject, right? In this topic, right? Value of mean stress, stress amplitude, and R ratio. So let us do a simple question that has been asked in GATE. A simple question, one mark question that has been asked in GATE 2019, right? So let us read the question first. During a high cycle fatigue test, we will understand what is a high cycle fatigue test later on when you study SN diagram, right? A metallic, but that does not mean that you will not be able to do this question. A metallic specimen is subjected to cyclic loading with a mean stress of 140 megapascal. Metallic specimen is subjected to a cyclic loading with a mean stress of 140 megapascal. So what is given is sigma mean is equal to 140 megapascal. And a minimum stress of minus 70 megapascal. So what is the value of minimum stress? Sigma minimum is equal to minus 70 megapascal. The R ratio is already given, minimum to maximum stress for the cycle loading. It's very, very simple question. Indeed, this should have been for 1 mark. Now, we all know that sigma average, that is mean, is nothing else but sigma max plus sigma mean minimum divided by 2. So this is already given 140. You find out sigma max. And this is also already given minus 70 divided by 2. So if you cross multiply, the value of maximum stress will come out to be 140 into 2 is 280. 280 plus 70 is 350. 350 megapascal. So what will be the value of R ratio? See, it is so good. They've already given you what is the meaning of R ratio. So they're not testing you for your knowledge. They're testing you mostly for your aptitude. R ratio is equal to sigma minimum divided by sigma maximum. So see, unless and until is written somewhere, magnitude, only magnitude, right? You have to use the full sign. So minimum stress is minus 70, maximum stress is 350. So this will come out to be minus 0.2. And this will come out to be minus, because 70, 150, this will become minus 1 by 5. This is minus 0.2. Basically, this is the answer. Right? So it is a very simple question, but indeed a very informative question. So this way, I end the demo for today's class, because if I start the next topic again, it will take at least 1.5 hours, right, to complete the whole topic for you to have a good understanding. Now this way, each and every topic will be cleared, right, and questions will be practiced. You'll be given assignments, your doubts will be cleared, and I hope you enjoyed the demo session, and I hope that you were able to learn something from this, and hope to see you during the classes. Thank you. For any more information, you can call us on the given number, or you can mail us, and you can visit our website, and you can go through all the information that is provided. And if any doubt, you can contact us on this given number. Also, please subscribe us for many more free videos. You can subscribe us in YouTube, right? So that you can keep learning, and we keep on providing videos, useful videos, and hopefully all those things will help you. Thank you. Good night. Take care.